Welcome back, everyone. I'm Akash Joshi. I'm the Operations Research Guru, and today we're going to be talking about representing linear programs as matrices. So, our first step will be to standardize the linear program according to the standardization rules. Then we will define the matrices, the parameters, and the variables. And third, we will convert the linear program that has been standardized into a matrix linear program. Okay, so our first step is standardization. I released a video on standardization, so please go check that out before you watch this video, but I will explain the basic concepts of standardization. So we have this linear program right here. We are minimizing our objective function. We have these two constraints over here that are limiting, that are upper bounding these variables over here. We have our sign constraints over here. X1 has to be positive, X2 has to be negative, and X3 has to be positive. If you want, you can go ahead and see if you can standardize this without my help using my video that I released a few days ago. So yeah, but here is the answer in case you didn't know how to standardize it. So the objective function, we are not going to change that at all. We are going to change this 2x2 to minus 2x2, and we are going to make x2 positive instead. For here, it says that all x's are positives. And then we are going to add our slack variable to close the gap between the left-hand side and the right-hand side so that it equals 5. And we are going to leave this alone, and we're going to add another slack variable x5 to close the gap between the left-hand side and the right-hand side of this constraint so that it equals 12. And all the rules for standardization are met. We have no negative signs on the right-hand side of our constraints. All the variables are positive, and we have equality signs. So yeah, that is the standardized linear program. So now let's go on to the next step, which is to define the variables, matrices, and parameters. Okay, so let's call the variable n the number of variables. We'll call the variable m the number of constraints. And we're going to call matrix C an element of the real numbers according to the variables. And this is going to be our objective vector. And this notation is kind of confusing, so this is just for formality. Really, it's kind of hard to understand this without understanding what the element symbol means, and also what this what this is doing at the top of the real number symbol. So really, you don't have to pay much attention to this for now. Just keep this in mind and remember to try and understand it. So yeah, so matrix C is going to be our objective vector, and it is an element of the real numbers according to the variables. And then um, matrix A is our coefficient matrix, and it is an element of the real numbers according to m times n, the variables times the constraints. And matrix B is our right hand side vector, and this is going to be an element of real numbers according to m, which is our constraints. So the standard form of a matrix linear program, even though we have already standardized our linear program, we should make sure that the linear program follows the rules of a standard form of a matrix linear program. They are the same, but it is always good to check and double check. So we are minimizing or maximizing C transpose times our decision variables such that A times x, our coefficient matrix, times our decision variable, is equivalent to our right-hand side vector. And we have our decision variables, all greater than or equal to 0, following standardization rules. Okay, our next step is to convert this linear program following these rules that I have laid out on the last page. Here is the answer. So how did I do this? Let me explain. So we have this minimization thing right here, and we're going to keep that minimization thing over here. We have our not coefficient matrix, sorry. We have our objective vector right here representing all the coefficients in our objective function. So this 3 is down here, the 4 is down here, the -2 is down here, and there should be a plus 0 x4 plus 0x5, but we leave that out because we're multiplying by 0, so it doesn't really matter. But it's important to include it in the matrix. We have a 0 representing x4 here and a 0 representing x5 over here. And we are multiplying that by our decision variables xi. So let's get into our constraints now. We represent our coefficient matrix as this. So x1 is represented as 1. x1 is also represented as 2 for our second constraints, and so on. Notice towards the end we have an identity matrix. This is a coincidence, but this could come into play later if once we perform operations with the matrices. And keep in mind that we are making this equal to the right-hand side vector, which is 5 and 12. So yeah, also remember that it's important to keep our decision variables positive. Okay, that's it for today. I hope you learned on how to convert linear programs that have already been standardized into proper matrix linear programs. Thank you for watching. Goodbye.